Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into Go data structures, a fascinating look at how Go handles memory and data representation. Let's start with the basics, shall we? The article begins by explaining basic types like int, int32, and float.
Right, and it's crucial to understand their memory layout. The diagrams illustrate how these are represented as single 32-bit words, highlighting the difference between int and int32, despite their identical memory footprint. The type system enforces explicit conversions, preventing accidental type mismatches, which is a nice safety feature.
Exactly. That's a key point. The article then moves on to structs and pointers, showing how structs are laid out contiguously in memory. Think point struct with x and y coordinates. They're right next to each other.
And the difference between rect1 and rect2 is illuminating. Rect1 uses point fields, while rect2 uses point pointers. This directly impacts memory layout and allocation. It's a powerful illustration of how Go gives you control over memory management.
Precisely. This control is a significant departure from languages like Java or Python, where memory management is largely abstracted away. In Go, you're in the driver's seat, which allows for fine-grained optimization. It's a trade-off, of course, requiring more understanding from the programmer, but it pays off in performance.
I see. It's interesting how the article then shifts to strings. The representation as a two-word structure, a pointer to the data, and the length, is quite elegant. The immutability of strings allows for efficient sharing of storage, making strings slicing incredibly fast.
Absolutely. That's a clever design choice. The article even mentions a common gotcha in other languages, where slicing a string might retain the entire original string in memory, even if only a small portion is needed. Go avoids this pitfall. It's a testament to the careful design choices made in Go.
And then there are slices. The three-word structure, pointer, length, and capacity, is another key concept. The distinction between length and capacity is crucial for understanding how slices work. Slicing doesn't allocate new memory, it just creates a new header referencing the existing data.
Right, and this efficiency is a major advantage. The article emphasizes that this design choice avoids unnecessary allocations and garbage collection overhead, leading to better performance. It's a beautiful example of optimization through careful design.
Finally, the article touches upon new and make, two functions for data structure creation. The subtle but important difference is that new returns a pointer, while make returns the actual data structure itself. It's a point of initial confusion, but it becomes clear with practice.
You're right. The article explains that they considered unifying these, but ultimately decided against it to maintain compatibility with C and C++ conventions. It's a good example of balancing innovation with practicality. This post only covers the basics, but it provides a solid foundation for understanding Go's memory model.
Indeed. It's a great introduction to the underlying mechanics of Go's data structures, and it sets the stage for future discussions on more advanced topics like interfaces, maps, and channels. I'm looking forward to those future posts.
Me too. Thanks for joining us on Tech Bytes and News. We hope you enjoyed this deep dive into Go's data structures. Have a great day, and we'll see you next time.
Bye-bye.